good. Okay, so is my screen visible?
Yes, sir.
Yes, sir.
Okay, so let us start. Okay, so what we had in the last class is a proof that the language consisting of strings of the form a power n, b power n, for all n greater than or equal to 0, cannot be regular. So what I will do, I will now state the pumping lemma in a formal form, and I would say in a most useful form. So it goes like this: let L be a regular language. Then there exists a positive constant k, a positive integer to be more precise, such that given any string let me write it this way: UVW in L with the length of V at least k, we have such that given any string UVW in L, such that this part, V part, is sufficiently long, we have the decomposition V can be broken down in 3 parts: X, Y, Z, satisfying 3 conditions. 1, the middle part, Y, is non-empty. 2, Y is not too long. Size of Y or the length of Y is no bigger than k. And 3, UVW have given, right? And V is broken, V is broken into X, Y, Z. I can pump in and pump out this Y as, okay, like this for all I integer greater than or equal to 0. So this is the formal statement. Okay, sorry, I should have W here. This is the V part. Inside the V part, I can take out Y once, or I can plug in Y, pump in Y as many times as I want. and the string still stays in the language L. Is that fine? So I am not going to prove it formally, but you can see we can take K to be the number of states of a deterministic finite automaton accepting L, and we can see how the states of that DFA evolve when it reads V. Sorry, reads this V, yeah, V. Okay. So at the beginning of V, it is in some state Q0. Then reading the first symbol, it is Q1. Reading the second symbol, it is Q2, and so on. And if the length of V is n, and after reading this n symbols from V, the state will be Pn. So I have Pn or Qn. So I have n plus 1 states, Q0, Q1, Q2 up to Qn plus 1. And n is greater than equal to k, so the number of states is greater than equal to k plus 1. So that means since the DFA has only k states, there must be a repetition, and that string, that repetition defines y. I can take it out, this y from V. The machine still reaches a final state. I can pump in y as many times as I want. The machine will still end up in the same final state. Okay, we have seen this. And a formal proof requires you to, I would say, handle the properties of the delta hat function for the DFA. Okay. So since we have done this proof already, yeah, tell.
Sir, what about finite languages, sir?
I will come to that. What about finite languages? In fact, this is the thing I would perhaps cover very soon. What about finite languages? The pumping lemma is still true. Okay. So, proof. Yeah, tell.
Sir, here what is the purpose of separately taking like U, V, W? Like in the previous class, we just took that V is a regular language, then we can break down V as X, Y, Z.
Yeah, of course, we have done it, but at the same time, we have seen that. Okay, so you just recall. So we first took W equal to A power K by 2, B power K by 2. Okay, and we had to solve 3 cases. So that Y, that is completely inside A, completely inside B, and consists of some A's and some B's. Whereas, if I took A equal to A power K, B power K, then if I take these as V, this as W, and U as empty, sitting just before this A power K block, then I am forcing pumping in or out in the V block. Okay. Therefore, only I needed to consider one case. Yes or no? Do you recall?
Yes, sir.
Okay. So this introduction of U and W before and after V sometimes say may simplify the proof significantly. Okay, so that is the reason why I am breaking inputs in 3 parts, and I am forcing pumping in or out in that middle part. Of course, I can take U equal to W equal to empty. That is also in mind. And in that case, I have a situation like this, and sometimes proofs become a little bit complicated. explicit form. Yeah, something is wrong. B. Okay. Okay, so the introduction of U and W, these are just for convenience in simplifying proofs. Okay. So we will see several other examples where we often, okay, so it's something like this, introduction of U and W, forces, pump in or out in V, and this may imply, of course not necessarily always, may imply proof simplification. Okay, so that's the only reason why I am stating this pumping lemma in the most general form. Okay, any other question about this? Then I will come back to a question raised by you. What about finite languages? But before doing that, I will add a note. First note is that while using the pumping lemma, forget about the DFA. This is an important thing. You just forget about the DFA, the proof of the pumping lemma. Okay. Instead, what you should do, and why forget about the DFA, I will come to that. Okay. That will answer the question of finite languages anyway. So in order to use the pumping lemma, you think of this as a game with a daemon. So these are the precise sequence of the steps. Daemon, and this is U. So step number 1, you want to prove that L is not regular, so assume L is regular. Okay, so you tell daemon, but I have assumed that L is regular. Okay, so for that matter, this now it's daemon's role to give you some k. Okay, so daemon declares the positive integer k. So from where this k comes, for hypothetical DFA or whatever, it's not your headache. Okay, daemon gives you some positive integer k. Okay, you can only assume that k is an integer, it is positive and a constant. Okay, so this is the second move. The third move is from you. You prepare some string U, V, W in L. Okay, so this is completely in your control. How you are going to start with the string U, V, and W, but you should ensure that the size of V, the length of V is at least as big as K. Because if you do not ensure that, the next of the game is meaningless. Okay. But whatever you choose for U, V, and W, it's completely up to you, but you have to stick to the rule of the game. That is by taking the size of V at least as big as K, whatever you have got. Okay. It's an abstract integer because, yeah, actually this K is a hypothetical number. Okay. Then what the daemon does, it gives you a decomposition of the middle part, that V part, X, Y, Z, and the daemon must also satisfy the rules of the game, that is, Y is non-empty, but no longer than K, and that thing, what is that? U, X, Y power I, Z, W must be in L for all I greater than equal to 0. So once again note that the daemon gives you the decomposition X, Y, Z. You have no control over X, Y, and Z. The only guarantee that the daemon gives you are these three conditions. Y is non-empty, no longer than K in length, I mean size, and this. So in the final stage of the game, fifth, you choose I for a contradiction. Okay, as the first proof illustrated, you may have to choose multiple I's if you want to handle different cases. So choose one or more I contradictions. So this is how the use of pumping lemma goes. Okay, so it's a kind of game with the daemon. Okay, you start by assuming that L is regular, then the daemon gives you K. What that positive integer K is, how the daemon gets this is none of your business. Henceforth, you never assume that K is obtained from a DFA. Okay. Then you prepared your input string and you have to satisfy the sufficiently long. Then the daemon gives you the decomposition. Again, you have no control over X, Y, and Z individually, except for these things. These guarantees supplied to you by the daemon. Then you choose your one or more I for arriving at contradictions in all cases. Is that clear? If you have any doubt, let me know. But this is the most important part, over which you have control, over which you do not have control. You have control over this assumption. You have control over this preparation of the initial string, and you have full control over choosing one or more values of I so that you reach a contradiction. You have no control what K is. You have no control what the exact decomposition is, because this is done by the daemon. Yeah, any query at this moment? No, perhaps. Okay. Okay. So consider this finite language. I will answer your query. L, let's say A, AB. So DFA for this can be drawn like this. If you read A, you go to a final state. If you read B, then also you go to a final state. Otherwise, there's a looping state which is not accepting. If you initially read B, you come here. If you read A, you come here. And if you read anything, the length 3 string, you also come here. What is the number of states for this DFA?
4.
4. So, number of states is 4. Okay. So, of course, you can take k equal to 4. Okay. And then everything is good. Okay. But the daemon gives you k equal to 3. In fact, we will see that no DFA with 3 states can accept this language. Okay, this is actually what is called a minimal DFA. Okay. But the daemon can give you k equal to 3. The pumping lemma still holds, right? Why? Can you tell me why? For k equal to 3, the pumping lemma holds for this language. Let us go to the earlier slide. So you assume that L is, sorry. Okay, L is regular. Daemon gives you k equal to 3, then it's your turn.
Sir, how will we prepare UVW because all strings have length less
You
than equal to-
cannot. Since you fail here, you cannot arrive at a contradiction. So it's your failure. The proof stops there, right?
So here you will say that pumping lemma holds true, like because it does not even start.
Yeah, what is the statement? Given any string, if you cannot give any string, then this is vacuously true.
Achha. Okay, sir, understood.
False thing can imply anything, whatever you say here. Okay. If you cannot produce this thing, whatever is written here, whether it is correct or false, I am the President of the United States, whatever you write here, this is the statement. This implies this is still true. Okay.
Yes, sir.
So for any finite language, I can take k to be 1 plus the length of the longest string in that language, which happens to be 2 plus 1, 3 in this case. So the daemon can give you k equal to 3, whereas no DFA with less than 3 states can accept this language. Therefore, I raise this note. While using this lemma, forget about the DFA. You just play this game. Is that clear?
One example is correct only because since we cannot give any string, we assume that the rest of the conditions are satisfied.
Yes, A implies B. This is the kind of thing. If there is a string UVW of length L in L with length of B, then this thing happens. If there are no such strings, the statement still holds. Agree or not?
Yes, sir.
Okay. So this is what is called vacuously true. Okay. So henceforth in all the proofs, unless explicitly needed, we will use this abstract game or this abstract form. We will not look into from where this K comes. Anyway, it is a hypothetical figure. Okay. So let us now see some examples, some more examples illustrating the use of the pumping lemma by forgetting the DFA. Okay, so this is our second, where am I here? So this is our example 2. Consider this, n square. So this is now our language L2. Okay. So every, I would say, pumping lemma proof, which is kind of, I would say, a game with the daemon, should start with your first move. What is that? Assume that L2 is regular. Assume or suppose that L2 is regular. Then the daemon gives you K. So the second line of your proof should be something like this. Let K be a pumping lemma constant for L2. Okay. So this is your first move. This is the daemon's move, but you are writing in your own language. Let K be a pumping lemma constant for L2. Next, what you should do, you should produce a string sufficiently long for giving to the daemon. Okay. So in other words, you have to choose U, V, and W. In this case, what I will do, take U equal to empty, V equal to a power K square, W equal to again empty. Okay. This is step 3. And you note that for a positive integer K square is greater than equal to K. So you are making this move as per the rules of the game. Okay. So K square is greater than equal to K for all K. Greater than 0. So whatever value you got as K satisfies this K square greater than equal to K. So the part of this V part is sufficiently long. And you should now proceed with the daemon's response. So the daemon gives you V equal to some X, Y, Z. Okay. And so we have a decomposition of the form B equal to XYZ with Y non-empty, not too long, and U, X, Y, I, Z, V is again in the language L2 for all I greater than equal to 0.
So it will be ZW.
This will be W. Okay. 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 Yes. Okay. Okay. So Now I take I equal to 1. Okay, and let's say the length of y is something like L. Okay, then, sorry, I equal to 1 is the original string itself. I will take I equal to 2. U, X, Y square, Z, W. U and W are actually empty. But if I pump in Y once, what string it will be? A to the power K square plus L. Okay. Now, this must be in L2. But is it possible? It is possible if L is 0, but L is not 0. L is at least 1. Okay. So K square plus L not equal to K square, since L is greater than 0. Moreover, what is K square plus L bounded from above? This is less than equal to K square. And the largest possible length of y can be K. This is strictly smaller than K square plus 2K plus 1, which happens to be the next square. So this K square plus L is sandwiched between two consecutive proper squares, K square and K plus 1 whole square. And therefore it cannot be of the form n square for some n. Agree?
Yes, sir.
Yes, sir.
Sir,
Oh.
can you please once show the third part of the demo?
This one.
Yes, sir.
They will give you a decomposition.
Yes, sir. Yes, sir. Got it, sir.
What exact decomposition it will give, this is not your choice. But you can rely upon these two conditions on the length of y and this thing. Pumping in or out condition. And then you choose I. Happy?
Yes, sir.
Good.
Sir,
Yeah, tell.
sir, that means L is not a regular language, right?
Yeah, so this eventually you again look at this, choose I for a contradiction or different values of R for different contradictions. And therefore, your first move that L is regular, okay, that is false.
Okay, sir.
Okay, so this is a proof by contradiction. You want to win, okay, by producing something called a contradiction. Okay. Yeah. So any question on this example? Then I will switch to a third example that potentially demonstrates the lemma in a more comprehensive way. Okay, so let us look at it. Oops. So example 3. So I take L3 similar to our L1, but I do something like this. Okay, so earlier I have taken this language to be a power n b power n, that is a power m b power n, where m is equal to n. And now I am taking m not equal to n. So is it the complement of that first language L1?
Yes, sir.
Yes?
Yes, sir.
No, sir.
No?
No, sir.
Why?
No, sir.
Sir, PA is in neither of them.
PA, for example, is neither of them. Okay. So be careful. The complement of L1 is definitely containing all strings of the form a power m, b power n with m not equal to n, but it also contains strings where a appears after b. BA, BAAB, all these things are neither in L1 nor in L3. Okay.
Sir, we can also say that if we say complement, then the empty string don't exist in L3, but it does.
Now please repeat. I didn't understand.
So you said L3 is complement of L1.
No, it's not.
Yeah, yes, sir. It is not. To prove that L1 and L3 both has this empty string.
That is also true. That is another way you can, yeah. Yeah. Yeah.
So how does L3 contain empty string? M is not equal to n.
Oh, I see.
L3 does not.
So it does not contain empty string. No, it does not contain empty string. But anyway, you can see that L3 is not the complement of L1. This is certain, right? No, epsilon is not there. Yes, you're correct. Yeah. Anyway, so I will apply the pumping lemma on this language. Okay. So once again, suppose L3 is regular. Let K be a pumping lemma constant for L3. Okay. Then I choose UVW. In this case, I choose epsilon. V equal to a power K. W equal to what? Okay, first let me do one thing. Sorry, not A, P power K plus 1. Okay. Let us say I choose this. So I am justified in this choice because V is of length greater than equal to K. Okay. Now that daemon gives me the decomposition X, Y, Z such that 1 less than equal to Y less than equal to K and X, Y, I, Z, U is epsilon, just put B power K plus 1 W, X is in L. Somehow,
Sir, why X twice?
okay, it is U, right? It is U. U. Okay. For all I greater than equal to 0. Now, in order to arrive at a contradiction, what I want, somehow I have to force equality in M and N. Okay. So already this K is smaller than K plus 1, so I can take something like I greater than 0. Okay. So take I equal to 1. Then how it will be? I equal to 2. In that case, it will be of the form a power K plus L B power K plus 1 is in L. For some L in the range 1 through K. And then you say take L equal to 1. You cannot say this. Because L is what is given to you by the daemon. It is not in your control. Do you understand why this proof is wrong?
Yes, sir.
Sir, can you repeat,
Yes, sir.
please?
Okay, so I take I equal to 2, then this pumping lemma guarantees that a power k plus L, b power k plus 1. And then you say I take L equal to 1. You cannot take L equal to 1.
Sir, what is L here?
L is the length of y.
Okay, sir.
You cannot take L equal to 1. So maybe you also talk about something like this.
Sir, if we change W to be like B to the K plus K factorial.
I'll come to that. But let me make some bad attempts. I will do that. Exactly, I will do that thing. Okay, good. So then you can say, okay, so the daemon give me L, whatever L. Okay, now I will prepare this tree. And replay the game with the daemon. Okay. This time, the daemon will again give you a decomposition of V into X prime, Y prime, Z prime. Such that the length of Y prime, which now I call L prime, let us call it L prime, will satisfy this. Okay. But daemon does not guarantee L prime is equal to L. If you continue to use that DFA analogy, you can take L prime equal to L. But just we have seen that this K need not be associated with the DFA. Okay, that is why I have given you this example, right? K is 4, but the daemon may give you K equal to 3, and therefore you should not think about the DFA. Okay, so once again, you are not justified in assuming that L prime is equal to K. So this is again another wrong way of using the pumping lemma. Are you with me? You must understand this very subtle things about the pumping lemma.
Sir, L prime does not depend on L, right?
You have given a different input string to the daemon. So it can give you a different decomposition of V because W is different. How the daemon operates is not in your hand, and that is the reason I am again highlighting. You have no control over this decomposition, and you cannot use the decomposition of one string in another decomposition if you play the game afresh. Okay.
Okay, sir.
Second time you may get different decomposition. Okay. So these two are common mistakes in pumping lemma proofs that we have seen over ages, over years. So no control, you never forget this, no control on Y, or for that matter, the length of Y. Not even on the length of Y, you have no control, except that it satisfies these inequalities. And third, and the second, do not think about the DFA. Do no longer think about the DFA. Okay.
So that means
Sir?
we have to find a contradiction for each XYZ where Y follows this condition.
Yes. So these are two unsuccessful attempts. I am trying to illustrate very common errors found in proofs that we have seen so far in our, I would say, teaching life. Okay. But the correct solution is already spelled out by some of you.
Sir?
Yeah, tell.
Sir, in the second one, how did we arrive at the contradiction? Sir,
I have not. That's why this is a big cross. This proof gets 0. This proof also gets 0.
sir, in this, the L we don't have control over L prime.
Yeah, so the proof
Like,
fails.
how does that mean?
The proof fails. I am supposed to prove this is not regular. So I gave you 2 unsuccessful attempts to prove it. Now I will do something where I will succeed. Okay.
Here are you saying L prime cannot be 1 or something in relation with L? I did not get that.
No. Daemon gives you a decomposition. You cannot take L equal to 1. Daemon gives you something. L may be 2, in which case you do not, arrive at any contradiction.
Yes, sir, that is the first one. And in the second one?
Second one, you now say, in order to win, so you now supply a to the power k, b to the power k plus L, where L you have got from the previous run of the game. Okay. But the point is that the daemon does not, work with a DFA or something like that. This time, because the input string is different, even if you assume that the daemon is deterministic, okay, it will give the same decomposition for the same input, but now your input has changed. The
Yes, sir,
daemon
like
may,
it will give some random L that may not be same as previous.
something different.
Okay,
And if L prime is different from L, then again it's possible that you do not arrive at any contradiction. Okay. So when you apply the pumping lemma, do not think about the DFA. Okay. Because K may be different from the number of states of the DFA. Okay, as we have seen. Okay. So how to supply a proper proof? So then you will see x equal to, sorry, not x. I will take u equal to epsilon, v equal to a power k. So I am faithful to the game, and I will take w equal to b to the power, somebody already suggested this, k plus k factorial. K factorial is anyway at least 1, so this is different from this. Okay. So now the daemon gives me a decomposition of the form b equal to x, y, z, and size of y equal to L, satisfying this. The daemon also lets me use the fact that u x y power I z w in L for all I greater than equal to 0. So now I take, this is completely my choice, I equal to k factorial by L plus 1, right? Plus 1. Because of the fact that L is between 1 and k factorial is a multiple of L. So this is an integer. Okay. So this is an integer. Okay. So whatever L the daemon gives, I can take I appropriately. This means I am pumping in this Y not once, but this many times. One occurrence is already there. The remaining these many occurrences I am pumping in. And then for this, what will be my U, X, Y power I, Z, W? This will be nothing but A power K plus K factorial, B power K plus K factorial, which is certainly, pumping lemma says it will be in L, but it is certainly not in L. Happy or not?
Sir, how come
So
that I is an integer?
Yes, yes.
Sir, how come that I is an integer? Can you just re-explain that?
L is between 1 and K, right? And K factorial is a product of all things between 1 and K.
Okay, sir. Okay, I got it.
Okay. To be more precise, I will just do this, just in case there is any confusion. Okay.
So, sir, in place of K factorial, we can put any multiple of LCM of 1 through K, right?
Yes, yes, yes. LCM of 1 through K will also do. Yeah. Okay.
Sir,
Yeah.
sir, what is Y here?
Why is some part of this? Why is some part of this, right?
Okay, sir.
So sir, if we had like the condition M not equal to N, if we did not have that, then will it be a regular set, regular language?
Yes, it is, because it's something like A star B star, right?
So can't we show that B will come before A in some case?
No, no. If I just do not I say n greater than equal to 0 without this condition, this is just the language of A star B star of a regular expression, right?
Okay, yes, sir.
Okay. Okay, so it's already past 1, so I think we should stop. And this language things, these are also important. So I will continue with this tomorrow, maybe for half an hour or something like that with the pumping lemma, and then we will start with DFA minimization. But you just tell me whether this is fine or not. Whatever L is, you win. You can produce an I. So this is now a fully correct proof. 5 marks. 0 in both the earlier attempts, 5 here. Okay. Okay, so let me stop. We will continue again tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank
Thank you, sir.